Okay, we have talked about common organic chemistry problems. One was fill in the reactions, the other one was draw mechanisms, and here is the one that students get hung up on the most. This is the design a synthesis problem. Now, at this point in organic chemistry, we don't have a lot of reactions. We're still very early in the game. And so neither of these synthesis pathways are going to be particularly complex. But what we want to be able to do is we want to be able to show some reactions where we that can lead from reactants to products. So how do we do that? Well, let's just look at one at a time. In the first pathway, the pathway from reactants to A, product A, what's happening? Let's think about it from a reverse position. I'm making an alkene. And so making an alkene means elimination reactions. Now, so when I think about elimination reactions, I can do an elimination reaction with a base, or I can do an elimination reaction with an acid. In order to figure out whether I want to do a elimination reaction with an acid or base, now I have to look at the reactant. The reactant is an alcohol. So I can't use a base because the alcohol isn't a good leaving group. I need to make the alcohol into a good leaving group in order for it to leave. So that's going to lead me to the acid consideration. So the reaction of H2SO4 with an acid can do elimination, but now I have to figure out, do I want the reaction to be concentrated H2SO4 or do I want it to be dilute H2SO4? Well, acid-base reactions are always equilibriums. We figured that out from earlier chapters. So I need to force the reaction into the products and away from the reactants. Well, what's another product? From the elimination reaction, we know that we have to eliminate water. Okay, if water is a product, then do I want to have dilute H2SO4 or concentrated H2SO4? Well, in dilute H2SO4, I have a lot of water present. And if I'm adding a lot of water, then I'm actually shifting the reaction away from the side of the reaction that has water. So I don't need dilute H2SO4. I need concentrated H2SO4. All right, so let's take a look at B. Well, this reaction's a little bit more complicated. Let's think backwards from product B and try to sort out what would the reaction be. Well, I know that I can get product B, and if I just glance up at the reactant, I realize there's also an inversion in the stereochemistry. So that tells me that I need an SN2 reaction. So I can do an SN2 reaction if I had a reagent that was a strong nucleophile. And I can have a strong nucleophile with a with this negatively charged conjugate base of acetic acid. So in order for this conjugate base of acetic acid to act as a nucleophile, I still need the alcohol to be a good leaving group. Now, in the previous example, we reacted the alcohol with acid to turn it into water to make it a good leaving group. That's not going to work in this case because that would be incompatible with the base. So I'm going to be reacting it with a relatively strong base, the conjugate base of acetic acid. We haven't done the nomenclature, but this is the acetate ion. So I'm going to react it with acetate, sodium acetate. Maybe you should know that from general chemistry. But if I react it with acetate, that's not going to be compatible with acidic conditions. So I am going to do this in the second step, but what am I going to do in my first step? I need to turn the OH into a good leaving group. Well, how do I do that? Well, I could react it with TSCl, a tosylate chloride in the presence of pyridine. That turns it into a good leaving group. Then I can react it with acetate to do the SN2 reaction. So recall, if I react an alcohol with a tosylate chloride, then I get OTS as a product with a retention of the stereochemistry. It does SN2 twice to get to this place. And so going from here to there with step 2 will get me my inversion in stereochemistry. Okay, there you go.